Hi, I'm Jeff Dusting, and I'm here to talk to you today about some thoughts I've had and some research that has been completed to look at the application of active risk management, the operation of tunnels, and the potential for that technique to improve tunnel safety. When we think about risk, we know three things. We know that we can avoid something bad, and there are things we can do to help reduce the likelihood of that happening. There are also things we can do to reduce the impact if something bad does happen. And we also know that both the likelihood and the impact varies over time. In transport tunnels, that risk varies with traffic density, the type of vehicles in the tunnel, the speed they're traveling, in ambient environmental conditions, is it wet, degraded visibility, and other elements. So the question I sought to ask is, why is it that we only calculate risk with rigor during the early design phases? Why is it that even though risk varies with time, we just assess it against some worst case conditions during the commissioning phase or design and commissioning phases of a project? This presentation summarizes some of the research that completed to answer those questions and answer the question, can we use the available traffic and maintenance data to determine the risk in real time? And importantly, would this be valuable to designers and to operators? It's a short presentation and there's a lot of research and underlying facts that sit behind what I present today. So feel free to reach out to me if you'd like to know some more details. The story is broken up into three parts. The first one, we visit what I've called the Italian story. The first time I came across others who'd thought about this idea was through some research published on PIARC and subsequent discussions with Salvatore Guia from Italy. Secondly, the research into the PIARC datasets, and then overlaying over the top of that, the concepts of a minimum equipment list, or the framework that's used in aviation to determine whether it's safe to fly a leg of a journey, and similarly, whether it's safe to continue to operate a road tunnel with degraded safety equipment. But firstly, it's worth recapping the risk paradigm or the risk model, and many of you will be familiar with the bow tie type framework, where on the left-hand side we have all of the mechanisms that we might put in place to prevent an adverse event occurring, and then we have on the right-hand side all of the tools we deploy to reduce the impact of an event. And I've applied a timescale on the horizontal axis here to show you that a lot of the prevention type work tends to be things that can be done a long way out. But also there are things that can be introduced in much tighter timeframes, daily, hourly, and even at the minute level to reduce the likelihood of an event occurring. We see that in our active traffic management plans that manage traffic speed, for example, at an hourly or minute scale to try and reduce the likelihood of major events during particular traffic conditions. On the right-hand side, we've got the response and the response once that adverse event has occurred. So this is where we see the fire detection and deluge systems coming into play, for example. And if you take that and do a little more, get a little more geeky and into your risk management, you'll know that on the left-hand side, the prevention measures quite often get considered in terms of the Swiss cheese model or the layers of prevention in a fire context that's often referred to as fire engineering. And then on the right-hand side, we have all of our protection measures, and the consequences are determined and quite often modeled using an event tree or a fault tree analysis, an event tree analysis, sorry. The other piece, and this I promise is the last of the geeky type slides to present, is that if you're looking to get a numerical assessment of risk, then you end up needing to take the probability distribution function of the events occurring, the consequences as a range of possible consequences in your risk model, and then you end up with a quite often plotted on an FN curve. The risk is modelled to determine where you are. And you'll see on those charts, I've got the dotted lines shown, which show the concept that there's not a black and white position for allowable risk. There's a range of acceptable risk for normal operations, and then heightened risk and so on. It's a sliding scale. So if we think back to this model, we tend to spend a lot of our time on in the D&C phase of our projects, focusing on event containment, so early detection, deluge, evacuation, etc. And in the D&C phase, we sometimes focus on prevention. So this is where we see safety and design, road safety standards and so on come into play. But this is where the operations has the more enduring impact on this left-hand side of the bow tie. So in operations, we know that risk varies, as I've said before, with traffic state and the driving environment, but also with the state of the protection and response equipment, the right-hand side. So it's not just the operational decisions, but it's also the decisions we make about maintaining our protective equipment. So if you have seen an FN curve, you'll know that these are quite often confronting curves or diagrams to see, where N on the horizontal axis is the number of fatalities and F is the frequency of those events. This plot shows the rate of fatalities for the road network in New South Wales. And obviously we want to be in the lowest possible part of these curves. Typically, when we certify a tunnel, the as low as reasonably practical region is the region that exists under normal traffic conditions and with all safety systems operating at full capacity. So, so with that context, I'll jump back to my Italian story. So the story in Italy at the time was that the European safety standards were being implemented with a 2019 deadline. And in Italy, there are a large number of old and aging tunnels that all met the threshold for improved safety requirements. But with a lack of money, the standards were focused on the right-hand side of that bow tie, applying deluge, fire detection systems, smoke extraction and the like to reduce the impact component of risk. But what they decided or proposed to do in Italy was to manage the left-hand side. So by actively managing the risk of an event, the likelihood of an event occurring, and managing factors within their control, speed, density of heavy goods vehicles, they were able to develop a model which they called Presto to demonstrate that they could keep these tunnels within the acceptable region without the need to spend the money on the safety systems. This model had some large data sets, but no live test data demonstrations, but was very informative in developing this concept a little further. So from there, we took the view that, yes, it is worth pushing this a little further, and let's have a little closer look at active risk management. And to think a little bit about, well, what was it that the Italian team were trying to do? If in the scenario here, we have elevated risk due to some traffic conditions or perhaps some degraded safety systems. And the question is, if I've got a heightened likelihood of an adverse event happening because there's a large number of heavy goods vehicles with dangerous goods loads, or passing through the tunnel at a particular time, or we've noticed a increasing level of lane weaving, then there are options for us, and we deploy this all the time from a traffic management point of view to bring us back into the acceptable region. But similarly, if there's a maintenance condition that exists for our deluge system or our CCTV surveillance system, where we're relying on those systems to reduce the impact of the risk, what can we do to reduce the likelihood and still keep us inside this acceptable region? And if we're monitoring and receiving this information on a real-time basis, then it allows us to do these things rather than resorting to disruptive response plans, and hopefully reduces the likelihood of some loss of life and major events. So the next step was to try and develop a demonstration that took some operational data sets and build up a probabilistic risk model. So can we connect the impact of traffic speed and heavy vehicles, the weaving index and the like, with the probability of an adverse event occurring? And then similarly, can we build out our models to show what's the relationship between the state of safety equipment on the impact of a major event? So when I say those quickly now, they're relative, they sound like they should be easy to do, but it's not a minor task. So to help there, I spent some time working with some others who looked at leveraging what was already in place from PIARC and Turismo. These data sets and risk evaluation models provide a framework so that you can take tunnel equipment, quantity and operating state, road operations data and statistics, which of course vary by jurisdiction, and a set of assumptions to be able to complete that risk evaluation and say, am I in the acceptable region or not? So the first question was, how is this going to work and help us in operations? Is it something that would be useful? Is it something that could be used to avoid traffic risks? Or is it something that we could use that if we had safety critical equipment that failed, that we could use to assess our risk, maybe reduce the traffic speed or volume and defer that major disruption to repair critical equipment to a less disruptive point in time? And secondly, does this help our operators who are left with managing risk without an awful lot of substantiated information? But once we started looking at this demonstration, the question that also occurred is, could we apply this in the greenfield context? If I could actively manage the tunnel operations within the acceptable region, could we redesign or would that have an impact on the design of greenfield assets? Could we end up with reduced redundancy requirements? So given that an operator has other tools to keep operations within that acceptable region, could we reduce the number of spare jet fans, for example, or overlap in CCTV cameras? Or, you know, is there an opportunity to reduce the redundancy level? Because we know that with active risk management, we can keep ourselves within the acceptable region by changing the traffic patterns. And would it help by reducing the overall cost So it's a question that has never been pushed a little further, and I think, as we all know, in the construction cycles, making a change to our design methodology comes with challenges, but it's perhaps worth rethinking these ideas. So the sample implementation. So the team from EcoExperts and Accurate took the idea that I put to them and developed a product that they called Dynamic Risk Manager. It takes those PIARC and Turismo models to dynamically calculate the risk based on the real-time traffic and asset state data, and provides a visualization to the operator overlay over their usual OMCS user interface, allowing them to monitor the state of the road in real time and its risk state. The tool effectively comprises a dynamic risk model. So on the bottom left diagram that we have here, there's a frequency analysis that takes those parameters, so the initial event and the incident scenarios, through a detailed event tree. They call it consequence analysis, or a version of that impact analysis that I've been talking about in the past, in order to then generate an expected risk value. Now, it's a little interesting in Australia because New South Wales has published their allowable limits from an FN curve perspective, but we don't have those nationally. And so there's certainly some work to make sure that we've got some agreed FN curves to model this into. And similarly, the fault tree probabilities vary by jurisdiction, and this model developed by EcoExperts has leverages heavily on data out of Europe, and the accident profiles in Australia are not necessarily the same as those in Europe. This is just a slide here to show how they went about integrating this idea into the control room, highlighting that the risk is shown in real time, and then when operations, a critical system fails and operational risk pushes outside the safe zone, or traffic conditions breach a threshold, then the operator is presented with a range of possible options to pull operations back into the green. It's a closer look to see how that went. Now, EcoExperts were then able to run a trial or a case study in Australia where they had access to historical data analysis and historical data, traffic data, plus the serviceability status of jet fans, axial fans, smoke duct dampers, deluge, heat detection and AID cameras, so effectively the fire life safety equipment. And we're able to look at that historical data to give a retrospective view of the risk, the active risk at various, at a continuous point in time over the term of that data set. And that historical data set was able to identify prior situations where the tunnel was operated at, let's call it heightened risk. It allowed simulation to validate both how effectively the model was projecting the likelihood of an event given particular conditions, and also simulate the impact on the risk profile of taking particular operator actions. And through this trial, they're also able to demonstrate that there was in fact value in leveraging this tool set for enhancing operational procedures. So rather than having a minimum equipment list that says when a jet fan fails, you close the tunnel, or you need more than one deluge zone to have become unavailable to close a tunnel, or whatever the operational rules are of that particular asset. You now have a continuous assessment basis that allows tunnel operators to verifiably keep the tunnel in the safe zone and balance that with disruption to traffic. So to me, this feels like a particularly valuable tool set and a framework that we should really be thinking about incorporating into all of our future control systems. And if we have the courage, perhaps you look at how this may be applied in the greenfield design environment, so that when we're assessing our fire life safety systems and criticality, we can consider both the dynamic management of risk rather than the simple static assessment of defined regulatory conditions. So that's all I have today. Thanks for your time, and if you have any questions, feel free to reach out to me. Thanks.